Okay, so the exam is set to next Tuesday, 3 to 6 p.m. And it will be 3 hours for you guys, but we will design it for a content of 1 hour. Okay, so I wouldn't worry about too much about it. Okay, all right, so that's about the exam. And the exam is going to be online. Okay, so we'll do the same format as we did before in the second exam. Now today, I want to go over some of the basic design problem for the column. And also want to talk about the type of problems you're going to see in the exam. So these are the content. I think today will be officially, okay, well, I got a few more students coming in. Maybe let me slow down a little bit. Okay, got waiting room, admit. Okay, admit all. Excuse me, okay. All right, I think I have most people here. Sorry, let me start over. So, guys, I just talked about it. I talked to Dr. Snee about it. The exam is next Tuesday, 3 to 6 p.m. It's going to be 3 hours. And we will design exam for 1 hour of lunch. So you have more than enough time to write your exam. And that's for that. And then for the today's lecture, we're going to talk about the design, column design a little bit more. And today is our officially last lecture. And Thursday, tomorrow, I still be here as more like open question review. And we will talk about the problem you will be seeing in the exam. And we can get into more detail today. And also, I'd like you to ask me questions maybe tomorrow after you've gone over the homework on the column part of it. So before I start, there's any question from you guys? Anything? Okay, all right, so let me start the sharing the screen so we can see the content here. Just 1 second. Oops, give me 1 second. Sometimes require me install this software. All right, so let's try it again. Okay, here you go. Okay, so this is the homework problem. Okay, you should have seen this. If you haven't, maybe you want to take a look at the homework number 11. And this is not collected again, but you can see the homework and start working on it before the exam. Okay, so this is the column shown, and it's a tie column, and we are supposed to differentiate between the tide and spiral. I put some reading materials into the folder. It's called column RC column read 1, RC column read 2. There you can find the difference between tie and spiral. For our intended purpose right now, especially for the exam content, we don't have to worry about it. Okay, so now for the tie, it tells you that clear cover to the tie is 1.5 inch. Essentially is this distance right here between the edge of the concrete to the edge of tie is 1.5 inches. Okay, now it's a number 3 tie, so you have to consider the dimension of the tie, which is number 3, so 3/8 of inch is the distance. So the real concrete cover between the top concrete surface to the bar, if I use the red color right here, this concrete cover right here, CB, should equal to 1.5 plus 3/8 plus half of the bar diameter. In this case, number 9 bar, so 0.5 inches. Okay, so that's first thing. You need to find out the concrete cover to get the position of the top compressive bars. Okay, now with that being said, you have a new thing that is in the middle, you have another layer of bars. We didn't talk about this, right? And then we have the bottom bars right here. Okay, so this is the geometry of the section, and the question is asking you first compute VMN, so VPN, VMN for pure axial compression, right? That's case 1. And then for strain diagram corresponding to a compressive strain of 0.003 on the top and 0 strain on the opposite surface, this is essentially 0 tension, right? We talk about this as essentially 0 tension. And then compute PN, VMN for balanced strain conditions, right? So this means epsilon S equal to 0.00207, given that this grade 60. And last one is compute PN, VMN for strain diagram corresponding compressive strain of this on the top and the tensile strain of 0.005. That means it is tension control the limit. Tension control limit. Okay. So this is clear. So why I want to put this problem out is because in the previous lecture, we did not cover the example with another layer of reinforcement in the middle. Okay, so the difference is actually not much. If we draw the strain diagram, and just take this picture from notes, and you can see that if I have center layer bars, on top of what we talked about before, I have compression from the concrete, compression from the first layer reinforcement, if I call it 1, and I also have a compression from second layer reinforcement. So how to determine that is you use the strain diagram, to find out the first layer of steel and find the strain of that, and also find out the second layer of steel, the strain of that. So there's no difference. The only difference is that you have to consider additional layer and find a strain corresponding and get your stress like we did from the previous example. Okay, now in terms of moment, you also have a similar situation where you have two, actually where you have additional moment now. So here, this I think missed one is actually, let me say the CS2X, okay, 3. Okay, so meaning that you need to have additional moment. But now look at this diagram here, okay? The definition of moment here, or where to sum the moment, is different. So in our homework, in our previous lecture notes, we sum the moment with respect to center of the section, right? So that means everything in terms of lever arm, everything is in the form of half h minus blah, 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 right? That means it's starting, or when you sum the moment, you're summing from the half h distance. So in that case, you do have to consider the moment from the additional layer reinforcement. Now the drawing here did not, because they sum the moment with respect to the compression force of the second layer. Okay, so they just cheated, so it'll be easier for it to sum it. Okay, you find a less summation basically. All right, so for our intended purpose, you can do either way, right? I strongly suggest you stick with our convention that always sum the moment, with respect to the center of the section. So this will be a consistent with what we did before in the previous selection notes. Okay, all right. So this is not too complicated. Try it yourself, and then if you have questions, we can address this tomorrow as well. Okay, I'll be here tomorrow during the lecture hours. Okay, all right. So any question on this, folks? Are we good on this? Anything, guys? All right, so I take it that you haven't started working on the homework yet. So please do that. You can start exercising it today. And if any question, best we can talk about it tomorrow, because next week we're gonna have our exam. All right. Okay, so this is about column analysis. Now, some of you may have a question, what type of problem you'll be tested during the exam on a column? I will have to say that configurations like this will be one of the typical test examples, tested problem from previous exams. And we'll most likely will just ask you guys to check the capacities. Check the capacity, meaning that you will compute the VAPN, VMN, and we'll give you a axial force and eccentricity to give you basically PU and MU. All you need to do is to make sure PU is bigger, smaller or equal than VMN, and MU is smaller or equal than VMN. Okay, so that's all we're going to ask you to do. Now, I mentioned that there are two axes. I showed you the previous exam we have two axes. In this exam, we'll try to leaning towards with one axis to cut down the confusion, okay, to cut down the confusion. So it will be easier for you, okay? So it'll be easier for you. I strongly recommend you exercise this problem, okay? I strongly recommend you exercise this problem for the exam. And if you have any question about the exam, let me know, okay? If you have any question about it, let me know. All right, so that is about the column design. That is about the column, analysis. I want to talk a little bit about the column design. Okay, so in the ACI, chapter 10, that is for column, chapter 10 for column, you find this diagram here. this interaction diagram here. So the green line here is the corresponding axial force and bending moment resistant line. And if we apply the strength reduction factor phi like we did before, you basically scale it back to this curve here. Now you notice that there's a dashed line right here and there's orange squared out area which is cut off from the dashed line here because I will have to enforce another coefficient, reduction coefficient alpha in front of it to cut it even smaller. And this is based on imperfection and buckling and all the other issues. Okay, so for now, all we want to know is that after we do the scaling down from the strength reduction factor, your acceptable design region should be within this orange shaded area. That means if my applied load in terms of PU and MU fall within the range, you're safe. If your design load fall outside the range, it's not safe. Okay, simple as that, simple as that. So we've been talking about this column forever, right? So it seems like you already got a good understanding of interaction diagram and such, but there's a critical issue here is that this design was done under a short column assumption, okay? Short column assumption. That means there's not much of buckling, there's no buckling, okay? And not much of a lateral deformation, small lateral deformation. Okay, how do we ensure that? How do we ensure that? We have to check. This is so-called a new definition is slenderness ratio. Okay, slenderness ratio. Okay, so slenderness ratio is defined as K, which is the restraining factor. Okay, restraining factor. Now, this restraining factor really depends on the boundary condition of the column. For example, if I have a fully fixed, right, K is about 0.5, sorry, K is about 0.1, 1.0. And if I have a half fixed, I have a different number, okay? And you can look it up. Now, this must be by L U over R. LU is the length of the column. And R is the radius of gyration of the column. Sorry. Gyration of the column. Okay, so essentially you can think of it, it is just the column size. Column size. All right, so the longer or the bigger this number is, the more slender the column is, and it is more easier to become buckled. So we do not use the interaction diagram. So as long as your slenderness ratio is controlled below these numbers, we can use the short column assumptions. Now, typically, we're dealing with short columns, okay? In the real construction for reinforced concrete design, very few cases will deal with longer column or slender columns, very few cases, okay? So most of the case, we're focused on the short columns, okay? So that's just one point I want to make clear, okay? So the second point in terms of design is that when you design a column, right, you don't go in and just start doing an analysis on the section and all that. You actually will rely on this interaction diagram. You will rely on this interaction diagram. So this interaction diagram is non-dimensional. So there's no numbers on it. Okay, so it start definition, and you can find this from ACI. So from definition of a section, you can see that I have a height on the right top here. I have the height, H, and I have a distance between bars as a gamma H, okay? Gamma H. That means I can tell you the position of the bars from here. And if I apply the axial load Pn and have an eccentricity E, and this will looks like is with respect to the neutral axis right here, okay? So that means this design or this chart is calculated based on this configuration, And you can plug the number in to get the section, but right now we can assume we don't know the section. This is just some relative ratios, and this is what we're seeing here. Okay, now one typical interaction diagram C here is shown on the left. Materials property is given, which is 4 KSI. Yield strength is given, 60 KSI. Gamma, which is the ratio between the distance between bars and the section height, is also given. Okay, so these are the set of parameters for this figure. You find a numerous figures just like this with different parameters. Okay, so now let's take even more detailed look at these figures. Okay, so going to this figure first, you see this x-axis, right? That is Rn, which is called moment coefficient, moment resistance coefficient. And this is a function of Pn, which is axial force, E eccentricity, divided by F prime C concrete compressive strength, a G gross section area, and H height of the section. Okay, so this is the definition of that. And it's non-dimensional, right? So you just have numbers in the x-axis. Now in the y-axis, you have Kn, which is the axial coefficient, right? And that is the axial force Pn divided by F prime C compressive strength and divided by the gross area of the section, entire section, which is Ag. Okay, now you start seeing these lines, solid lines in this chart, right? So let's take a look, right? What are these lines representing for? So essentially each line like this, for example, represent the interaction diagram for a particular reinforcement ratio. All right, so you see here there's a rho epsilon equal to 0.08. That means this has a reinforcement ratio of AST divided by AG equal to rho equal to 0.01. Okay, 0.01. So if you were given the bars like this, and mind you that the bars have to be in the same configuration as this, it doesn't have to be exactly 3 bars, but has to be symmetric, okay, and then has to space out between each other gamma h of distance, okay, gamma h of distance. Now with that, if you were given a design that you can calculate the reinforcement ratio, you can just go in to find this corresponding interaction curve like this, so you don't have to compute it. Okay, all right, so now you can see that these are lines, and further you see that it divided by several zones, right? So there's zone 1, zone 2, zone 3, zone 4, 5, 6, 7, 8, 9, 10, etc., so on and so forth, right? So how do they define these zones by these straight lines, right? In other words, what are these straight cut-off lines are for, right? So remember that back then, last lecture, we talked about this is like point A, and somewhere like a point B, somewhere like point C, where is it? C here, and point D, and point E. Remember, this is how I label it. And you notice how I label this because now here, this is corresponding, actually B is wrong. Let me just correct that. B is here. Okay, these lines or these points corresponding to what? Corresponding to the strain in steel, in tension side of a particular, okay? So you notice that this is basically Fs divided by Fy. That is the stress in the tensile side of reinforcement divided by the yield strength of the bar. So when Fs divided by Fy equals 0, that means there's no tension at all in the reinforcement. So this is not exactly the B we were talking about. We talk about B in terms of there's no tension on the concrete, but this is very close to that. Okay, this is very close to that. Then you go on down to the row, and now I increase more stress in the steel, all the way till this point. That means Fs equal to Fy, and this is so-called a balanced failure, if you remember, right? This is called a balanced failure. So at this point, I have point C. Now keep going, and I reach that. If I clear this out, I'm sorry, cover it, but this is where I have reached the epsilon t equal to 0.05. So this is tension controlled limit. And then go all the way down when across the x-axis, that is the point E. Okay, so you don't even have to compute the critical points on this interaction diagram. It pretty much tells you already. Okay, so the power of this design or analysis diagram is essentially tells you that if you design a section and you provide a reinforcement and geometry, you can use this non-dimensional diagram to construct your interaction diagram in terms of numerical numbers. Okay. Sorry, folks, I have the problem with my internet, so let me just reshare my screen. Don't know what happened. Let me see here. Can you guys still hear me? Are you guys still there?
Yeah.
Okay, sorry about that. There's some internet disconnection. Okay, so if I have given the cross section of the column, right, and then given the reinforcement and tell you the position of bars, I can basically come into this diagram to directly obtain my interaction diagram. There's one interesting phenomenon here, okay? There's one interesting phenomenon, that is the width of the column is not given. You don't have to provide a width for the column, okay? So in this diagram, there's no need to provide a width of the column. All right, everything has been normalized. Everything has to be normalized. That is, though, whenever you want to get a real force and moment, you have to compute with the number of width, right? With the values for the width you're assigned for. Okay. All right. So that's that. That's that. All right. So I want to also mention one thing, and there's a coefficient in front of the axial force, P and max. Now we did not talk about it. This is basically based on the stirrups. Is it tie or spiral? And also slenderness ratio, okay? And for all intent purpose right now, we don't have to worry about it, this number too much. Right now, I just want you to know that we always use Pn equal to phi and 0.85 F prime C Ag minus AST plus Fy AST, like we did in the previous example, okay? Folks, I don't know why this is happening. I think my Zoom just coming in and out. Are you guys, can you guys still hear me?
Yeah.
Oh,
Yeah, we can still hear you.
okay. But the screen is no longer shared, right? You cannot see the screen anymore, I take it? Okay, let me try it again. I'm sorry, I don't know what happened with this internet thing. Try it again. Okay. Can you guys see the screen now? Is it on, guys?
Yes.
Oh, okay, good. Okay, thanks. So let me just continue. Sorry about this. I just don't know what happened this morning. But all we have to do in the exam and in your homework, remember this equation, okay? I don't want to get too complicated. Okay. Now in actual design, I have uploaded a example on the Canvas, so you can take a quick look at it. And if you have questions, we can discuss about it. But for now, for the exam, we just do where we'll test you guys on the analysis part of only, okay? Testing on the analysis part only. All right, so now, last but not least, I want to talk about this detailing of the concrete columns, okay? So normally when you have concrete columns, right? So there are several ways to construct it. One is that you may just get a foundation, okay, or footing, and you have to bury those bars in like this, okay, in like this, and these bars will stick out. These bars will stick out, right? And then you have to build another bars straight up, straight up, straight up, and straight up, and overlap, overlap, okay? And this is the splice length, okay? This is splice length. And that is equivalent to the development length we talked about before. Development length we talked about before to develop enough tensile stress in the bar. Okay, so this is not a bad thing, but the critical thing is how you pull this reinforcement. Okay, so here it shows in the detail in the ACI code that you need to offset the bars. Okay, offset the bars. How to offset the bars? So the black bars are the bars in the footing, right? That means the black bars, the footing bars, stays inside. Okay, stays inside, and the column bars stay outside. Okay, like the drawing here. Okay, the column bar stayed outside. All right, and the main reason is that I'll provide enough concrete cover. I'll provide enough concrete cover for my for my column bars. Okay, for my column bars. All right. Okay, so these are some details that I want you to know. And for the design part, I put some reading materials in the folder, and please read that if you're interested. As I said, for the intended purpose exam, we're not going to test on the design part. But later on, if you have a question on design, we can talk about it. Okay. And there's a full example on Canvas about the column design. It's not sophisticated. Once you understand how we do analysis, it should be easy to follow through it. Okay, easy to follow through it. All right, I think this marks the end of the lectures and also end of the semester. I'm very happy to have this privilege to work with you through the semesters. And I will stop here and welcome for any questions, okay? And you can also stay behind if you have any other questions. All right, let me stop recording. Okay. All right, let me do